Insulated redundant grounding conductors in patient care areas should be bonded to the box. This requirement stems from several important reasons. Firstly, the National Electrical Code, specifically Section 517.160b, mandates this practice. This section clearly states that the insulated equipment grounding conductor shall be bonded to the grounding terminal of the receptacle. Secondly, bonding the insulated grounding conductor to the box significantly reduces the risk of electrical shock. By creating a low-impedance path, fault currents can flow more readily. This rapid current flow helps to quickly trip circuit breakers or ground fault circuit interrupters, minimizing the duration of any potential shock hazard to patients or medical personnel. Thirdly, this practice aligns with the recommendations outlined in the Institute of Electrical and Electronics Engineers, or IEEE Standard 363. This standard specifically recommends bonding redundant ground conductors to the box to enhance patient safety and maintain the overall integrity of the electrical system. It is important to differentiate insulated redundant grounding conductors from isolated ground receptacles. Isolated ground receptacles are designed for specific applications where isolation from the general grounding system is necessary. These receptacles have a dedicated grounding terminal that is not connected to the standard grounding conductor, and they are not subject to the same bonding requirements. However, insulated redundant grounding conductors are used in conjunction with standard grounded receptacles. They provide an additional layer of protection by establishing a redundant grounding pathway. Therefore, it's crucial to bond them to the box in accordance with both the National Electrical Code and IEEE Standard 363. To reiterate the importance, National Electrical Code Section 517.160b requires that the insulated equipment grounding conductor be bonded to the receptacle's grounding terminal. This bonding process establishes a robust and reliable grounding system that minimizes the potential for electrical hazards in patient care environments. By adhering to these standards and recommendations, healthcare facilities can ensure a safe and effective electrical system for both patients and staff. Let's delve into why a low-impedance path is so crucial. A low-impedance path allows for a greater magnitude of fault current to flow in the event of a ground fault. This higher current helps to quickly activate overcurrent protection devices such as circuit breakers or fuses. When these devices trip quickly, they interrupt the flow of electricity to the faulted circuit, minimizing the duration of any potential shock hazard and reducing the risk of damage to equipment. Now let's consider the implications of not bonding the insulated grounding conductor to the box. Without this bond, the grounding path may have a higher impedance, which could limit the amount of fault current that can flow. This could delay the activation of overcurrent protection devices, potentially exposing individuals to a longer duration of shock hazard and increasing the risk of equipment damage. Understanding the role of IEEE Standard 363 is also important. This standard provides guidance on the design, installation, and maintenance of electrical systems in healthcare facilities. It emphasizes the importance of redundant grounding to enhance patient safety and electrical system reliability. By following the recommendations in IEEE Standard 363, healthcare facilities can create a more robust and resilient electrical system that minimizes the risk of electrical hazards. In summary, the requirement to bond insulated redundant grounding conductors to the box in patient care areas is based on sound engineering principles and is supported by both the National Electrical Code and IEEE Standard 363. This practice is essential for creating a safe and reliable electrical environment for patients and medical personnel. Neglecting this requirement could compromise the effectiveness of the grounding system and increase the risk of electrical shock and equipment damage. The grounding system is an essential safety component of any electrical system, and its proper installation and maintenance are critical for protecting individuals and equipment from electrical hazards. In patient care areas, where vulnerable individuals may be connected to sensitive medical equipment, the integrity of the grounding system is even more critical. The use of insulated redundant grounding conductors and their proper bonding to the box provide an additional layer of protection that can significantly reduce the risk of electrical shock and ensure the safe operation of medical equipment. Therefore, It is imperative that healthcare facilities adhere to the requirements of the National Electrical Code and the recommendations of IEEE Standard 363 to ensure the safety and well-being of their patients and staff. Think of the electrical system as a tree. The main service is the trunk, the branch circuits are the branches, and the grounding system is the root system. A strong and well-connected root system is essential for providing stability and support to the entire tree. Similarly, a robust and well-maintained grounding system is essential for providing safety and reliability to the entire electrical system. The insulated redundant grounding conductor acts as an additional root, providing an extra layer of protection in case the primary grounding path is compromised. By bonding this redundant grounding conductor to the box, we ensure that there is always a low-impedance path for fault currents to flow, minimizing the risk of electrical shock and equipment damage. Therefore, it is crucial to understand the importance of grounding and to follow the proper installation and maintenance procedures to ensure the safety and reliability of the electrical system. The National Electrical Code, or NEC, serves as the cornerstone of electrical safety in the United States. It is a comprehensive set of standards that provides detailed requirements for the safe installation and maintenance of electrical systems. The NEC is updated every 3 years to reflect the latest advancements in electrical technology and to address emerging safety concerns. It is essential for electricians, engineers, and other electrical professionals to stay up to date with the latest edition of the NEC to ensure that they are following the most current safety practices. The NEC is not just a set of rules, it is a comprehensive guide to electrical safety that is based on years of experience and research. By following the NEC, we can minimize the risk of electrical hazards and create a safer environment for everyone. IEEE Standard 363 is another important resource for electrical safety in healthcare facilities. This standard provides specific guidance on the design, installation, and maintenance of electrical systems in hospitals and other healthcare settings. It addresses the unique challenges of providing electrical power to sensitive medical equipment and protecting vulnerable patients from electrical hazards. IEEE Standard 363 emphasizes the importance of redundant grounding, equipotential grounding, and other safety measures to minimize the risk of electrical shock and ensure the safe operation of medical equipment. By following the recommendations in IEEE Standard 363, healthcare facilities can create a more robust and resilient electrical system that minimizes the risk of electrical hazards. Equipotential grounding refers to the practice of bonding together all exposed conductive surfaces in a patient care area to create a common ground potential. This helps to minimize the voltage differences between these surfaces, reducing the risk of electrical shock. Equipotential grounding is particularly important in areas where patients may be connected to multiple medical devices, as it helps to prevent the flow of current through the patient's body. The NEC and IEEE Standard 363 provide detailed requirements for equipotential grounding in healthcare facilities. These requirements specify the types of bonding conductors that should be used, the methods of installation, and the testing procedures that should be followed. By implementing equipotential grounding, healthcare facilities can significantly reduce the risk of electrical shock to patients and staff. Regular testing and maintenance of the grounding system are also essential for ensuring its continued effectiveness. Grounding systems should be inspected periodically to identify any signs of corrosion, damage, or loose connections. Ground resistance measurements should also be taken to verify that the grounding system is providing a low impedance path to ground. Any deficiencies that are identified during these inspections should be promptly corrected to maintain the integrity of the grounding system. Proper grounding is an ongoing process that requires continuous attention and effort. By investing in regular testing and maintenance, healthcare facilities can ensure that their grounding systems remain effective in protecting patients and staff from electrical hazards. Let's discuss some common misconceptions about grounding. One common misconception is that grounding is only necessary for protecting equipment from damage. While grounding does play a role in equipment protection, its primary purpose is to protect people from electrical shock. Another misconception is that any ground connection is sufficient. However, the quality of the ground connection is critical. A high-impedance ground connection can actually increase the risk of electrical shock by limiting the amount of fault current that can flow. It is essential to ensure that the grounding system is properly installed and maintained to provide a low-impedance path to ground. Another misconception is that ground fault circuit interrupters, or GFCIs, eliminate the need for grounding. While GFCIs are an important safety device, they do not replace the need for grounding. GFCIs detect ground faults and quickly interrupt the flow of electricity, but they do not prevent ground faults from occurring in the first place. Grounding provides a low-impedance path for fault currents to flow, which helps to prevent GFCIs from tripping unnecessarily and ensures that they will trip quickly in the event of a ground fault. It is important to use both grounding and GFCIs to provide comprehensive electrical safety. In conclusion, the requirement to bond insulated redundant grounding conductors to the box and patient care areas is a critical safety measure that is supported by both the National Electrical Code and IEEE Standard 363. This practice reduces the risk of electrical shock to patients and medical personnel by creating a low-impedance path for fault currents to flow. It is essential for healthcare facilities to adhere to these standards and recommendations to ensure the safety and well-being of their patients and staff. Proper grounding is an ongoing process that requires continuous attention and effort. By investing in regular testing and maintenance, healthcare facilities can ensure that their grounding systems remain effective in protecting patients and staff from electrical hazards.